Okay, so at a particular temperature, K equals this value right here for the following balanced reaction. We have a reaction. So in an experiment in which 1.5 moles of SO2 and 1 moles of O2 are mixed in a 2-liter vessel, what are the equilibrium concentrations of all gases? First off, it's actually kind of a jerk move for them to give you, this equation isn't actually right if this number's right. It should have an equilibrium there. Yeah, they do the, they do, but it should have an equilibrium if this number was accurate at all. So it's kind of a weird thing to do. Anyways, we can still do this. It doesn't matter. So this is a nice problem, right? Okay. And so you should go ahead and set this up like a nice problem, right? In which case you have your reaction. You go ahead and write your K with your equilibrium expression next to it, right? So your K equals 1.8 times 10 to the negative 6, but that also equals your equilibrium expression, which is, well, products to the power of coefficient. So product right there to the second power, right? You can use a concentration in this case because we don't have partial pressures, do we? Okay? We have something that's much easier to get into concentration. Moles and liters, right? So, concentration's fine. Notice we have K, which K with nothing next to it typically means a concentration, doesn't it? Okay. Okay, so again, that's the product SO3 to the second power divided by SO2 to the second power, again, coefficient is 2, and O2 to the first power in this case. Yeah, everybody's good with that, right? Yeah. Notice that nothing's a pure liquid, pure solid. We don't have to worry about that. Okay, next thing we do is we have to go ahead and figure out our initial concentrations, don't we? We weren't given initial concentrations, so we're going to have to figure them out. How do you figure out a concentration? Well, that is what over what? Huh? No. Concentration in molarity would be moles over liters. Very good. I'm really going to scar it into you one of these days if you don't. Moles over liters, right? You should start chanting it before you go to bed. Moles over liters. Moles over liters. This is your new... Yes. This is your new counting sheet before you go to bed, right? Okay, so whenever you have a concentration, you put a 0 next to it, that means that times 0, right? And it's another way of saying initial concentrations. So we take 1.5 moles, which is what we were given. It's divided by 2 liters because it's a vessel that's 2 liters large. Gases expand to fill their vessels, right? So that has to be our volume. And that gives us a molarity for that. The O2 is the other thing we were given. And so we take 1 mole divided by 2 liters, and that gives us our molarity, 0.5. The SO3, we're not given any, so it can't have any, right? That's going to be made in the reaction. That will be made during our equilibrium. Okay, so we go ahead and list off initial change equilibrium, our ICE table, right? Because now we have initial concentrations we can work with. So we have our reaction. Notice that we've represented it as an equilibrium now, because that would actually be a good way to do this. Because it is an equilibrium, right? All right, our initial concentration is what we just figured out. So 0.75, 0.5, right? And we don't have any of the product. Well, our change has to be our reactants getting used up, doesn't it? And we have to make products. So again, for every 2 of these we use, we'll use one of these, and that will give us two of these. Does anybody have any problems with doing that? Like when you're doing that, are you having any issues? Because there's other ways I can describe it and help you understand, but it's such a ubiquitous concept that you've seen had so many times at this point that I usually just skip over. Okay, again, our initial minus whatever we used up, right? And so our initial minus what we used up. And then our equilibrium out here, initial minus what we used up again. And then whatever we produce is how much product we have, right? Okay. Now that we have these values, we're going to go ahead and plug them into our equilibrium expression, aren't we? So we plug these into our equilibrium expression. So 2x goes in that up there. This right here is this number right here, 0.75 minus 2x. And this 0.5 minus x is right there. Notice the second to second power, okay? Mathematically, that would make this pretty damn hard, wouldn't it? But let me ask you a question. So x has to be something proportional to that number, right? Notice whenever you solve these, it's something that's on that order, right? Usually within one order of magnitude of this k number, isn't it? Okay? It's like if you get a 10 to the negative 6, this stuff up here is not 10 to the positive 6. It's 10 to the negative 5, 10 to the negative 7, you know, something in that range, right? Yeah. And so if that x is some number that's near 10 to the negative 6, what would happen if you took 0.75 minus a number in that order? Minus a 10 to the negative 6 number? You would just round it right back up to 0.75, wouldn't you? Wouldn't make any difference at all. So that's typically what's referred to as the 5% rule. If you have one number that's less than 5% of the other number, usually it's less than your rounding errors anyways. And so what you can do is you can essentially say, well, subtracting or adding that number doesn't do anything. It's insignificant, right? So I can just take that minus 2x here, get rid of it. Because even if I minus that 2x, I'll still have around 0.75, right? And I can do the same thing for the minus x. So 0.5 minus x is still going to give me about 0.5, right? So these numbers down here become just 0.75 and 0.5. I don't have to worry about the minus x portions. Okay? Notice, what does that do to my values here? I don't have any x's there, do I? So something that would have been a lot of work to solve becomes really easy, doesn't it? Because I make that assumption. Okay, so now I have 0.75 squared, I have 0.5 to the first power, and on the top I have 2x squared. I can simplify that top a little bit by calling it 2 to the second power, which is 4x squared. Okay, and now I'm going to go ahead and solve for x. You could do the math in individual pieces, like you could do 0.75 squared times 0.5 down here and simplify this portion. But I'm just going to do it the variable way, okay? So I multiply over 0.75 squared, and that ends up over here, right? I multiply over 0.5, and that ends up on the top, on the other side. I then divide over 4, and that will end up on the bottom, right? And that leaves me x squared equals those numbers like so. I then go ahead and do my math. So 1.8 times 10 to the negative 6 times 0.75 squared times 0.5 divided by 4. That will give me what x squared is. I have that little answer. I bring my answer down I don't get rid of it. I don't round it. I then put it to the 1/2 power. Another way of saying that is I square root it, right? I personally prefer doing it to the 1/2 power. I just think it's easier. Okay? And that gives me 3.558 times 10 to the negative 4. So that means my x is 3.558 times 10 to the negative 4, right? I go ahead and plug that into my numbers above. So I go ahead and plug it into one of them and see, was my assumption correct? Because remember, I made an assumption to make my math easier, didn't I? So I plug that in. I find out that I would get a number of 0.7493. Yeah, I'd round that back up to 0.75 in most cases, right? It's 9 right there. That would be 0.095%, by the way. If you're less than 1% difference, you're doing great. Like rounding error is typically about 1%. So you try to avoid it, but all right. So our assumption was good, wasn't it? So what does that mean? Well, our SO2 concentration, it's approximately 0.75, right? Our O2 concentration, it's about 0.5, isn't it? 0.50. And finally, our SO3 concentration, well, that is 2 times that X number, right? So 3.558 times 2 gives you 7.1 times 10 to the negative 4, right? Notice I didn't mention the 10 to the negative 4. You don't have to work with the 10 to the negative 4. If you multiply it by 2, you can just take the 3.55 times 2. That gives you that. Okay. If you want to double check it, by the way, you can. You plug your numbers in here into your K expression, solve it for K, and notice you get the same number. So, yeah, we did a good job. That's how you can always double check your answer before submitting it, okay? You can always plug all your numbers in directly into the equations and see if you get the same answer out as what you were given in the first place. Okay, does anybody have any questions about that? No? Okay. All right.